exercises, okay? But you know, I'm perhaps, you know, if I have a couple of simple exercise that I can figure out, I give and post on Dropbox to you, okay, as appended at the end of the slides, okay. You know, I try to write nicely during the Christmas time, okay, so that, you know, you can study those 2-3 exercises, okay. So I give you a couple, 2-3 typical exercises. But you know, I mean, this part is similar to Kalman, which is, you know, I mean, the only exercise, the only real exercise that I can do with that is by making homework or similar. I'm still thinking if doing the homework about this part, you know, which was my original idea. Right. So if you do some homework on this one, you learn, okay? Because you learn like you was learning about the boundary condition, okay? So you learn by solving the homework in any case. So, you know. Anyway, so let's look at the multiple signals. So, you know, imagine that I have multiple signals, okay? By the way, when I say multiple signals, it's multiple features. So, you know, S1, S2 can be, you know, is representative of a vector collecting different features, okay? I prefer to call it signal because, I mean, mentally, for me, is more easy, but this is a vector. So, you know, what's happened for multiple classification for multiple signals? So, multiple signals are, you know, I have a set of classes, H1, H2, and Hk. And then I have X is equal to S1 plus W, S2 plus W is K plus W, depending on the different condition. So, now, if I look at the probability condition, the probability of X, which is the data, condition to each individual class, it is a Gaussian. By the way, Gaussian is because it's easy. Gaussian is because the formulation comes easy. But the life is not always Gaussian. Okay? So, you know, perhaps, I mean, when you start doing something, I mean, you face that it's not Gaussian. Don't be surprised. The life is not only Gaussian. It's only because if it is Gaussian, it's more easy. If not, you know, it's getting a little bit more complex. Now, going to the point. So, assume that this set of states, okay, these are sets of, you know, hypotheses, and each of that is Gaussian with a certain mean, which is given by the signal. Classification, you know, is for, you know, searching which hypothesis is more likely. So, how do I make it? You know, I make essentially the following way. If I assume, okay, now this is a strong assumption in some setting, but if I assume that all classes are equally likely, we remove this assumption later. But if I assume that are all equally likely, then, you know, my decision is in favor of one class with respect to another, only if, you know, the corresponding likely, which is the corresponding probability, is greater with respect to another. So this, you know, this is by using the probability of X as a likelihood function. Okay. So if I make a ratio, you know, you can make a ratio between, like here. So it's like to say Px given Hk is Px given Hi. So if this one is larger than 1, then I decide for Hk. If it is lower than 1, I decide for Hi. Okay. So then, you know, if I have multiple decisions, then I start searching, okay, one with respect to all the others. So I'm searching which class has the corresponding highest probability. Okay, so I search one in favor, so H1 versus H1 versus H2, H1 versus H3, and so on. Okay. Now, if I make the log accurate, it comes out that this inequality becomes this inequality. So, you know, I decide in favor of HK if the distance, the distance between X and SK is minimum, if it is weighted by the inverse of the covariance. So this is the weighted norm, okay? Just, you know, to recall you that if I write A minus B with a norm W, this is equal to A minus B transpose W A minus B. Okay. So this is the weighted, the norm of the weighted norm. Okay. So you can read this definition together. So that means that, you know, I decide in favor of SK if X is closest to SK, if the distance is closest to SK, weighted, okay, with respect to the inverse of the covariance. And so, you know, that means that I search of the distance, weighted distance of any value with respect to all the other points. So in 2D, if I make in 2D, that means that I have a point, okay? So this one is S1, this one is S2, S3, blah, 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 and this is S capital K. Okay. And so, you know, that means in 2D, this is a 2D case. Okay, so, you know, and imagine that I have one measurement. So one measurement, you know, maps into here, and this is X. Remember, we are two-dimensional plane. Okay? So this is X1, and this is X2. Okay? So, you know, I need to calculate the distance. So this distance here is S is X minus S1. This is S minus S2. Okay. Now this is the distance. Now this distance is weighted. Is weighted by the inverse of the covariance. Okay. So you know it's difficult to put. So you know this distance is scaled with respect to the noise, the property of the noise. Now, so if I am in a very special condition, and this special condition says that the covariance is equal to the identity. So that means that is the case that the telecom says white Gaussian noise. Okay? So I have a set of signals in white Gaussian noise. Now those signals, like in communication system, are the point of the constellation, which is like the corresponding waveform that I'm using to transmit. So then when I blah 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 manipulating that, then the test hypothesis is that I have the SK transpose X minus the norm of the signal, and I decide in favor of HK if this one is larger than the other. Now since I need to decide with respect to many, because I need to decide the distance between X1, X2, and X3, so I need to make the decision one with respect to all the others. So then a very common way to describe is the following. So the input is multiplied by the local signal. So I make by this multiplier the inner product between S1 transpose X. Okay? So you know this multiplier makes the inner product, and the last one is S capital K transpose X. Then that's here, this is the multiplication. So all that. Okay, S1 transpose X, and this one makes S capital K transpose X. Okay. Then I remove, this term is dependent on the energy, so I remove this term, and then I search about that one, the one that is maximum. So I'm searching for the maximum one. Now this is the optimum classifier. Okay? So you know it's the optimum classifier in a class with the K signals. It's called correlation with receiver, right? In the digital communication.
Last chapter.
Is it?
Yeah.
Okay. Now, you know, so far we're in a condition where we know the distribution and we know everything. Okay. But in practice, this is not the case. So, you know, in practice, what we have that the probability density function of X under the case HK, okay, it depends on a set of parameters that depends in turn with respect to the set of parameters that belong to a specific subset theta K. So now you know, here we are mixing decision and estimation. Because I'm not saying that the parameter, actually here, when I say that, I say, you know, HK means that I have a specific signature. But you know, in practice, imagine that I have a radar system. Now in the radar system, in radar, the signature might be delayed and it might have a specific amplitude. And so that means that the existence or not of an echo depends also on two additional parameters, which are amplitude and the delay of the signal. This is an example of radar. Now, so that means that the problem starts getting complicated, but real. Okay. So that means that when I say that I have a signal X that depends on HK, and HK is a class HK, I'm saying that X depends on theta, and theta belongs to a subset of capital theta K. Now, so what is the capital theta K in general? Okay, is a partition of the total set of parameters, potential parameters. So in such a way that, you know, if I look at the parameters and I look at the intersection of different parameters, the intersection is zero. There is no intersection among the parameters corresponding to the classes. Now, let's say I have an echo, and the echo with the amplitude 0, which is a noise only, okay, belongs to a class which is different from the echo which amplitude different from 0. So now the class is the parameter amplitude larger than 0 and the parameter amplitude equal to 0. So larger than 0 and equal to 0 are two classes. Now, how to do that? Okay, the way the system, I cannot use the Laplace ratio test because I don't have the probability density function. So what? Now the most intuitive way is, if I have a system and I have a probability density function of the corresponding signal under the two conditions, I can estimate the parameter under the two conditions. Now that means that what I do is this. So I can calculate the Laplace ratio test in such a way that I find the maximum of theta belonging to the set theta 1 of the probability density function of x for parameterized with respect to theta. You know, actually, this one is the maximum likelihood estimator for theta belongs to capital theta 1. Now, and is the ratio between the other one, and the other one is the maximum likelihood estimator for theta belonging to theta 0. Now, to simplify, you know, theta 1, capital theta 1 can be the presence, and capital theta 0 can be the lack of signal. And when presence, there is the amplitude of the echo that is larger than 0. Then you know this is a disjoint set. And okay, so then you know after doing that, I replace the probability with a corresponding estimate of the parameter theta under the condition 1 and the parameter theta under condition 0. And I calculate the likelihood ratio test subject to the fact that I estimate a set of parameters theta 1 and theta 0. This is called generalized likelihood ratio test. So the generalized likelihood ratio test is the likelihood ratio test for the parameters that have been estimated. Let's make a couple of examples that are familiar to you. First, imagine that I have a sinusoid. You know, I conclude with these two examples. Okay. So imagine that I have two sinusoids. I have an example where I have one sinusoid or noise. Okay. So the hypothesis one is that I have a sinusoid with amplitude A0, frequency omega 0, phase of phi 0 plus W, or I have W home. Okay. So I have a sinusoid in noise. I don't know if there is a sinusoid. So how to make the generalized ratio test? Now, the set of parameters in this case, okay, the set of parameters in this case is the set of amplitudes, frequency and phase, which are possibly all. What is the set of parameters here? Set of parameters here corresponds to the empty set. Okay? So now you know I'm testing the likelihood ratio test after estimating amplitude, frequency, and phase of the sinusoid. So that means that theta, okay, for the hypothesis H1, theta are the set of parameters of sinusoid, which are amplitude, phase, and frequency. So under the condition H1, the model is x equal H, depending on omega 0, and alpha. You remember alpha is amplitude and phase together. Okay? Plus W. The other case is W home. Now, in this case, I can calculate the PDF. In the other case, the PDF depends on these two parameters, and these two parameters are not known. Okay? So now, how to get the maximum, the generalized likelihood ratio test? The generalized likelihood ratio test says, let me copy here, says that, you know, I need to calculate the maximum with respect to theta 1 of the probability of x, given that theta belongs to the set of theta 1. Divide by the max with respect to theta 2, theta 0, of the probability x, depending on theta, belongs to the set of theta 0. But you know, this one is empty. And so that means that my optimization reduces to the optimization which is described there, which is I need to calculate the maximum of the Gaussian with respect to cycloparameter theta. This maximum for the cycloparameter theta means that I need to plug in place of omega and alpha the maximum likelihood estimate. So, you know, there is an intermediate step here. That means I need to take off the signal, I need to make the maximum likelihood estimation of theta, which is equal to amplitude, frequency, and phase, okay? Which means, you know, after the maximum likelihood estimation, I get A hat, omega hat, phi hat. Once I estimated that, I plug into there, and I can calculate the likelihood ratio test. So there is an intermediate step of estimation procedure. Now, let's make it, because we know how to make it, because we know that to estimate the frequency of the sinusoid, the frequency of the sinusoid, we look at the maximum of the Fourier transform to the square, which we know it's called periodogram. So the maximum of the periodogram is the estimate of the frequency of the sinusoid. Good. So, you know, how is it? Now, if we assume, for instance, if we assume that the power spectral density is white, okay, so our goal reduces simply to that. So the generalized likelihood ratio test is the ratio between the maximum value of the periodogram, okay, for any omega, because that is the estimate of the frequency of the sinusoid, divided by the power spectral density of the noise. And I need to search it whenever this is larger or smaller than a threshold. Now, from the experiment, if you remember, we found that, you know, this means that by the periodogram, okay, so I have the periodogram of the noise, this is minus pi. I have the periodogram of the noise, and you imagine that there was a small sinusoid here. You don't see it, okay? And so, you know, the more the number of samples grows, and the more this guy is pushing out. Okay? So then, you know, increasing n, this one is coming out. Okay? So, you know, what it's saying is that this generalized likelihood ratio test says that, you know, you need to put a threshold here, that if putting a threshold here, if I see a peak that is larger than the threshold, that means that there is a sinusoid. If there is no peak larger than this threshold, there is no sinusoid. Now, operatively, it is very simple. Okay? So, you now probably understand why I put a question in some of the periodogram exercise where I ask you what is the minimum value of the number of samples of the periodogram to guarantee that this amplitude is a certain percentage of the noise. And the reason is because that is the sense to find out the detection of the sinusoid in noise. Okay? So now what I encourage, I write here, what I encourage is, since it is this way, so now look at exercises and exams on periodogram and search for the number of samples such that, I don't know, the power of a sinusoid is larger than the power of the noise by a certain amount. That certain amount was a threshold. You know, since in the past years I was not doing this part of the detection, so that question was almost, let me say, not clear for the students, because they say, why should I calculate the number of samples in such a way that this amplitude is large enough? And then, you know, the reason was that. Okay. Let's make the second exercise. And the second exercise is the following. You have a radar system. So our radar system, you know, we need to detect the target. Now this is a practical system, you know, so we don't have a system where, for instance, ideally the amplitude was constant. Now we have a system where the amplitude is alpha and the delay is tau, okay? Which is, you know, a very typical radar system, just to recognize. So you have a transmitter or a sonar, like a sonar, okay? You have a target, okay, and so, you know, you are bouncing back, and here you have a receiver, okay? So it's going this way. Now, I mean, it's important to see if there is a presence or not of a target, okay? If there is an airplane, if there is something and so on, okay? Now, so the amplitude and the time of delay, they depends on the kind of experiment, okay? So the amplitude depends on the target, okay, if the target is very big, okay, and the time of delay depends on the distance of the target. So now, you know, our likelihood ratio test cannot be done in this way, because, you know, I cannot describe the probability density function for H1, because it depends on parameter alpha, which is not known, and tau, which is not known, okay? Now in radar jargon, sometimes you, rather than estimating the time of delay, you do the windowing, which means you do a window and you check if within the window there is a signal that is larger than the noise. Okay, but that's an old strategy, I would say, many years ago. Now the generalized ratio test is carried out in this way. So I start with the likelihood ratio test, and by the likelihood ratio test under two conditions, you know, I have an alpha and tau. Now, alpha and tau, you know, are unknown. So what I should do is, I should maximize, let me see if I have it. Oh, okay, I made the whole manipulation. So, you know, what I should do, let me cancel that. Okay, so, you know, the way I do is, I want to find the max of that function, so right here, the max of this one with respect to alpha and tau. Okay, so it's similar to that case, where, you know, I need to maximize with respect to the numerator because the denominator was a noise, and so, you know, there's no way to maximize because I'm checking versus the noise. So now maximizing with respect to the numerator is something that we did. So, you know, we need to estimate the time of delay, and estimating the time of delay given the knowledge of the waveform, which is g of t, is carried out by the cross correlation. So all the manipulation that I'm putting in place is that I'm calculating the log likelihood with the numerator part, and the log likelihood, okay, and so, you know, and I'm searching here, I'm searching for alpha and tau. So, you know, the tau is the value that maximizes this value. So the log likelihood, the generalized likelihood ratio test is simply by pulling this part into the denominator, then the denominator is the other, okay? And so I need to maximize that one with respect to tau to find the time of delay. And so this reduces to this formula. So I need to find the arguments, I need to find the value when the cross correlation is maximum. That amplitude is compared to a threshold. So simple that. So I take the maximum of cross correlation, okay, and I compare with the threshold. Where the threshold, it depends on the waveform and so on. That's how it is. So, it's ultimately it's simple. Okay? So, in two cases, either estimating the frequency of the sinusoid and then pulling inside the parameter, which comes out that I search for the maximum of the periodogram, or looking at the maximum of the cross correlation between the signal and the received, or the signal X, and the replica, local replica of the waveform G, searching for the maximum, square, and compare with the threshold. Both methods, they are implementing the generalized likelihood ratio test. And I don't have any other. Let's see. Yeah, I don't have any other for now. So, Friday. Okay, Friday we conclude this part. We put the slides on Dropbox, I guess. So we conclude with the clustering and with the Bayesian classification, which is useful for understanding the set of data, set of parameters, where a set of data where you don't know exactly the features of the parameter. You are trying to understand from the data how the data are being built. Now going to the workshop, that means that in the workshop, I think one of the five, the last five was with the music, where you had a different label classifying the instrument. Okay. Now, rather than having that label, you don't have that label. So you need to understand how many instruments you were playing. That means you need to understand from different ensemble signals how many different instruments you can find. That means that you are understanding how many clusters of features you can extract from the data. And then once that, you classify the new data out of the training in such a way that you map the new data into the features that you extracted from a set of features where you did not know that there were how many instruments? Three? Okay. So you don't know that there were 3 instruments. You just get those signals. And then you try to understand that how many instruments, how many different instruments you can find out. Probably you get more than 3. Okay, so that was that is my suggestion. You can exercise yourself. Okay, see you Friday.